We present Shape from Release, a method for designing 3D printable tablets that dissolve at controlled rates. Our work is inspired by the emerging pharmaceutical 3D printing industry, which has the potential to personalize therapies for individual patients, but is currently limited by the lack of design software for optimizing tablet geometry. We specifically tackle the challenge of controlling the release profile of a tablet by optimizing its topology. In other words, we control the amount of drug that dissolves into a solution over time, which can be visualized with the concentration versus time plot shown here. Release profiles are important because the safety and efficacy of treatments often hinge on the rate of release. A tablet that dissolves at an inappropriate rate for a patient will not confer the full benefit or may cause harm. For instance, a better outcome may be achieved by a 3D printed tablet with a constant rate of release, as reflected by this constant slope cumulative release profile. However, designing 3D printable single material structures to release at these precise rates is a challenging open problem. We propose an efficient topology optimization solution for this inverse design problem that we call Shape from Release. Our computational method for designing controlled release structures consists of, first, a simple and efficient simulation of the dissolution process based on a geometric abstraction of the physical system. Second, an inverse design method posed as a PDE-constrained topology optimization. And third, a set of strategies to ensure that our designs can be directly fabricated. Bringing our designs into the real world requires accurate characterization of materials and calibration between physical and simulated quantities. To perform these calibrations, we developed a low-cost, image-based system for measuring dissolution over time. We also use this system to validate our simulation model and inverse designs. To design structures achieving a target release profile, we must first develop an efficient and differentiable dissolution simulation. Past approaches have ranged from molecular dynamic simulations at the small scale to larger scale Monte Carlo models. We propose a more efficient and differentiable approximate model based on geometry that nonetheless proves sufficiently accurate for design. Our approximate simulation calculates the volume released after the tablet dissolves to a depth of tau simply by constructing a distance field u from each point to the boundary, then evaluating an integral. By repeating this calculation at each depth, we can construct a simulated release curve. Shapes of low genus, like spheres, cylinders, and tori, shrink in surface area as they dissolve. This means that their instantaneous dissolution rates decrease over time, and their cumulative release profiles all exhibit negative curvature. Achieving constant or even increasing surface areas requires more intricate, sponge-like geometries that we create with topology optimization. Our topology optimization works by optimizing continuous variables that represent the material density or infill fraction of each cell in a grid. This requires generalizing our simulation to support variable density objects, which we do by solving a variable speed iconal equation where the dissolution speed is determined from the infill density using a simple interpolation law. The solution field tells us the dissolution time of each point, and then we can again calculate the release curve by evaluating an integral. Our topology optimization then uses this simulation and its gradient to improve designs to better match the target release profile. We include additional objective terms to promote binary designs for single material fabrication and to ensure layer-by-layer fabricability. Here's an overview of our topology optimization process. Starting from an initial design guess, we compute the dissolution time field and calculate the simulated release curve. We then measure the deviation between the simulation and the target profile and use our gradient formulas to improve the design by updating the density field. We repeat this process until convergence, watching a crisp, optimal shape eventually materialize. Due to our fabrication constraint enforcement, the final design can be directly 3D printed. We fabricate the designs generated by our inverse design method on a consumer-level FDM printer using a water-soluble filament. These are some photos of our fabricated prototypes next to their digital counterparts. In order to establish a relationship between our simulation model parameters and the units of the real physical system, we employ a calibration using a custom measurement setup. This setup is also used to evaluate the performance of our printed designs. We validated our inverse design system on a variety of target release curves and with different strategies for enforcing printability. The orange designs on the left were not constrained to be printable. The middle designs in green were defined by extruding 2D density fields into 3D, guaranteeing printability by construction. The right designs in yellow were created by incorporating a physics-based printability objective in the optimization, as described in our full talk. We are able to achieve constant rate release profiles and even increasing dissolution rates with our optimization. Please watch our full talk to learn more.